our last class we were talking about some of the problems related to floor planning, and we also looked at one of the methods or algorithms that have been proposed to solve the problem, namely using integer linear programming. Now, today to start with we talk about an interesting method which relies on some concepts of graph theory, the concept of a dual of the graph, and starting from the concept of slicing a given floor plan, we can have the concept of a slicing tree, and we will see that the slicing tree and a floor plan have a one-to-one correspondence. So, let us have a look at this method first. So, this method is called rectangular dual graph method or approach. Now, the basic concept is quite simple. See, when you are carrying out a partitioning of the circuit, because this floor planning and partitioning are typically carried out hand in hand. When you are dividing a circuit into two blocks through partitioning, so what we expect is that with respect to the floor plan, there one of the partition A will be placed in some region and the other partition will be placed in a disjoint region. So, the output of the partitioning algorithm can be represented by a graph. Okay. So, there will be a graph where the nodes will indicate the different partitioned submodules and the edges will indicate their interconnections. And in this method, starting from that partition graph, we can directly get the floor plan by converting it into its rectangular dual. We will see what rectangular dual is. Now, rectangular dual of a graph can be obtained, well, we will just show an example where each vertex in the graph will correspond to a distinct rectangle or a block, and if two blocks are adjacent, the two nodes will be connected by an edge. So, I am just showing an example to illustrate this point, where each vertex in this graph will correspond to a rectangle of the floor plan, and two rectangles which are adjacent, the corresponding nodes will be connected by an edge. Okay. So, let us see an example. Suppose I have a floor plan like this, and this is the so called partition graph, or the, you can say, the triangulated, sometimes this is called planar triangulated graph, also PTG. This is essentially the partition graph, which, well, actually I have shown this after this, but actually this is the starting point, and from this we want to get the floor plan. But here I am showing the correspondence. Suppose I have a floor plan like this. So, corresponding to each rectangle of the floor plan, there will be one vertex. One will be 1, 2, 3, 4 and 5, and the two rectangles which have some common area of intersection, region of intersection, they will be connected by an edge, like 1 and 3 are adjacent, 1 or 4 are adjacent, 3 and 4, 1 and 2, 4 and 2, 4 and 5, and 2 and 5, you get this graph. So, from the floor plan you can get this graph very easily. Similarly, from this graph, if you know the sizes of the blocks, you can also go towards this, and there are algorithms for doing that. Now, in order to do this, one thing is clear, is that you assume that there are no cross junctions in the floor plan. Like cross junction means 4 blocks connected like this, A, B, C, D. So, we will see later if there is a cross junction like this, what does this mean with respect to the dual graph. Because why we say this is that the success of this algorithm relies on a graph where all the faces of the graph, this is a planar graph, it can be laid out on a plane, because this is a planar representation. So, the vertices you are connecting by an edge, there cannot be two edges crossing. So, this will also be a planar graph. So, the success of this method relies on one premise is that the face of each region in this graph will be a triangle. That is why it is called planar triangulated graph. But the problem with cross junction is that you will get a graph which is not triangle faced. The graph will be like this: A connected to B, B to D, D to C and C to A. Okay. So, we do not want graphs like this, because graphs like this will lead to some problem in translating from here to here. So, we take an example to illustrate how, starting from a circuit, we can just arrive at a floor plan. Just we start with an example circuit. Well, I am not showing the exact circuit say in terms of gates, but rather I am saying that after partitioning is done, A, B, C, D, these are the partitions. So, I am actually showing the partitioned picture after partitioning. Suppose you have something like this. Suppose you have an example circuit like this, where A, B, C, D are the blocks which have been obtained after partition, and this shows the interconnection. Now, this circuit can be represented by a graph. This is your so called graph model, which you can get immediately from the partition circuit. So, here the partitions will be represented as vertices, and if two partitions are connected, they will be joined by an edge. Well, this can be a weighted graph also, indicating the number of connections which are there. From D and B there is a connection. Fine. So, you can say this graph is already triangulated. So, all the faces are triangles. Now, from this graph model you can draw the corresponding rectangular dual. So, rectangular dual is a graph where corresponding to each vertex you will get a rectangle, and two edges, I mean two vertices are connected in an edge, means the two corresponding rectangles will touch at least in some non-overlapping area. So, one such rectangular dual, this is again not unique, one such rectangular dual for this graph is A, D, B. You see, of course, the exact sizes of these will depend on the width and height or the areas of these things in terms of the number of components there. So, I am assuming that A is the biggest, A takes the biggest area, B is bigger than D and so on. So, this is one possible floor plan. You can see A is adjacent to B and D, B and D, D is adjacent to A, B, E, D is adjacent to A, B, E, C is adjacent to B and E and so on. So, there are systematic algorithms to convert a graph model into the rectangular dual. We are not going into that algorithm, but you can see that it can be drawn. So, if it is a planar triangulated graph, then this translation can be done fairly easily. Okay. But as I said, if there are cross junctions, then the algorithm for translation can create some problem. So, we try to address that problem. So, the first thing is that we have already seen that if the floor plan does not have any cross junction, then the corresponding graph model is a planar triangulated graph, and also the reverse, vice versa. So, since in the early example, for example, this was a PTG, planar triangulated graph, this is one triangle, this is one triangle, this is one triangle, then we get a rectangular floor plan without any cross junctions. But if there are any cross junctions like this, well, then means according to the normal thing, you will get a graph like this 1, 2, 3 and 4. See, although 1 and 3 and 2 and 4 are very close together, they are touching at the corners, but still you do not show any edge in the graph. See, interconnecting 2 and 4 or 1 and 3 may also be very easy, because they are touching, but here you are not capturing that. So, normally what is done if we have a cross junction is that, I am showing it indirectly, actually it will happen from the other side. So, you shift this block slightly on some sides, for example, if you shift it like this, you shift 4 a little bit on the right, so that 4 and 2 overlaps a little. So, now you will get a graph like this with this new edge added. Now, if we have a graph like this from your partition circuit, then you find out that this among this 2 and 4 and 1 and 3, which are the ones which are more strongly connected among themselves. If you see 2 and 4 have some wires among them, well, they will obviously be connected, but if not, you add some dummy edge in order to make it triangulated. So, in order to make it if you make it triangulated, it is easy to convert it to this, that is the thing, because the algorithm which is there, that can very easily convert this into a corresponding floor plan, but if there is non-triangulated faces, then it can create problem, because in general it can be faces of sizes 4, 5, 6, so it creates a problem in making the layout. See, for 4 is fine, suppose you have a graph like this where there are 5, so what do you do about this? So, just without leaving some blank space in between, you cannot lay them out. You cannot have a very nice packed layout for this. So, for this it is mandatory to have a triangulated form first, and then you try to convert it into the rectangular dual. But there are yes.
So normally in a problem we go from a graph to its dual, or
graph to a dual, like I have just shown in this one. From the partition circuit you get a graph, from the graph you get the dual. This is your floor plan.
So here in the circuit, the arrows mean the interconnection.
Arrows are the interconnections. Blocks which are interconnected, they are shown by an edge. Now, in this example, this is already triangulated. If, for example, D and B were not connected, we would have forcibly added this edge or edge between A and E. Fine, but there are some exceptions. This is one exceptional structure that can occur in the graph. You can see in this is a complete graph of 4 vertices. Here all the faces are triangles, but yet you try to draw the corresponding rectangular floor plan, you will not be able to do that. There will be conflicts, you will see. This structure is called a complex triangle structure, and this does not correspond to a rectangular dual. You cannot construct the rectangular dual for this. Yes.
If 1 and 3 are connected and 2 and 4 are also connected, so then we cannot make a shift like this.
We cannot make a shift like this, yes. That means we will have to have some priority, I mean we will be taking this, yes. See, we will be just adding some edges if required, we will be removing some edges in order to make all the faces triangle. Yes, true. So, starting from the graph, the first step is to have only triangulated faces. The second problem is that if there is a complex triangle, you will have to handle this. So, now let us see if there is a complex triangle, how we can handle this. So, the methods, well, see, this method is very easy to understand, but the problem is that this is based on some graph theoretic approach, the some of the steps of which are still not very easy, like for example, from a given arbitrary graph how to convert it into triangulated one, and from the triangulated one how to have a very efficient algorithm to convert it into floor plan. Well, from small examples you can do it by hand, but for very complex examples it is difficult. But the main concern is if there is a complex triangle, what to do. The idea is fairly simple. See, your total graph may contain several such complex triangles, say 3 such. So, you try to break the complex triangles. How? We break the complex triangles by adding a dummy vertex to one edge of each of the complex triangles. We will show how. So, we add a vertex and an edge also, we will see how, to each of these complex triangles, as a result of which we eliminate the complex triangle structure. Well, I am first showing an example, then I will again come back to this. Suppose so we have a complex triangle like this. So, this is a complex triangle, and means what we do is that we convert this into an equivalent triangle where we introduce a dummy vertex out here and a dummy edge connecting D and this. So, we get a modified graph which looks like this. So, this new vertex we are calling E. E lies between B and C, okay, and a new edge between D and E. So, now the new graph becomes like this, which is nicely triangulated, 4 triangular faces, there is no complex triangle, and if you convert this into the rectangular dual, you get the corresponding floor plan also. So, one possible floor plan is this. So, you can basically check C is adjacent to ADE, ADE, A is adjacent to BDC, B, D and C, and so on. So, if there is a complex triangle, you identify the complex triangles in the graph, and for each such you add a dummy vertex and an edge to it. This E is actually a dummy one, it does not make any meaning, but this E you can merge finally,
There will be a blank space.
blank space. But by introducing this, you can have a properly triangulated one for which the dual exists. Means you can get a floor plan, but if you do not do this, you cannot get a floor plan from this, right. Okay. But the problem is that for a given arbitrary graph, identification of complex triangles in it, this itself has been shown to be an NP-complete problem. Okay, so this method, although apparently it looks fine, but implementation wise it is a complex problem, right, fine. So, what people normally do, they either go for a hierarchical approach or they go for you can say a randomized algorithm like simulated annealing. So, in hierarchical approach is fairly simple in concept. This is based on a divide and conquer approach. Divide and conquer, why? Because at every stage we consider only a few of the rectangles and their relative orientations and placement. It is possible that the original subproblem will be having thousands of rectangles, but at any particular level of our means of our algorithm, we consider only a very small number of rectangles. Okay. Just to show you, suppose you have a very small such interconnection graph like this ABC, these are the 3 blocks. From this graph you can have several different floor plans, just to show. So, if you have a small graph which you are handling, so for this graph you generate the all possible floor plans which are feasible, you estimate the costs of each and you select the one which you feel is the best. Now, after this is done, what is done at the next level of hierarchy, these vertices A, B, C are merged together into a super vertex. So, you start with small subcircuits, you try to obtain the best relative means the best relative placement or floor plan of those, you merge them into one. Now, this entire thing becomes a single rectangle. Now, at the next level this entire thing will act as a rectangle which you want to place. So, in this way, so actually from bottom you go slowly towards the top. Okay. So, in this example, as I have just said, that after an optimal configuration has been determined, they can be merged into a bigger module, and similarly the vertices will be merged into a super vertex at the next level. This process will go on. Now, the problem which I had mentioned earlier, that depending on the number of modules you consider at each level, the number of possible floor plans increases very rapidly. Just I am showing a couple of very simple examples. Well, I am not starting with any graph, I am showing all possible floor plans of 2 blocks. If there are 2 blocks, you can have either this or this, 2 possibilities, but for 3 you see that there are so many possibilities, 1, 2, 3, 4, 5, 6. So, for 4 it again goes up, for 5 it is very large. So, as the value of D is increasing, the number of possible orientation of the relative orientation of the blocks also goes on increasing. So, typically for this kind of a divide and conquer approach, where we are exploring all the possibilities at each level and try to find out the best, limiting D to a low value is very important. Typically D equal to 5 is the maximum you can have. So, as a rule of thumb we can say that D will always be less than 6. So, at each level we would be exploring all the possibilities exhaustively, because since the exhaustive search space is limited, we can do that, and we will be finding out the best solution depending on some cost function at each stage. Okay. Now, this hierarchical approach can operate bottom up or top down, both. Bottom up is the most natural. So, first let us look at the bottom up approach. Bottom up approach, as I have just mentioned, it is essentially a bottom up approach. The individual modules or blocks will be represented as the vertices of a graph, while edges represent connectivity. Now, you start by putting the modules together. You identify a set of modules. Suppose you have the parameter D equal to say 4 or 5, something you have chosen, say D equal to 5. So, your first task will be to choose 5 blocks which are most strongly connected among themselves. This you can easily find out by analyzing the graph. So, the modules with high connectivity you try to cluster together. Of course, restriction is that number of modules in cluster should not exceed D. Now, just as I mentioned, that after doing this, you exhaustively search all possible floor plan among those D blocks and try to find out the best, the optimal floor plan. Then at the next higher level of processing, the clusters are merged into a larger module. Moreover, with respect to the floor plan, the floor plan you have obtained, that rectangle is kept intact. So, that entire rectangle will be placed somewhere at the next higher level of processing. So, from the leaf you slightly you just successively go up by putting the modules together and again. So, finally, when you reach the root, you have a single node which is a union of all the blocks, and that node will represent your total floor plan. So, in this approach, as you move towards the, you can say, the individual blocks, the leaf of the nodes towards the root, your floor plan is getting constructed slowly, step by step, okay, in a hierarchical fashion. Now, means one simple way of implementing is to have a greedy procedure. So, you sort the, so instead of searching the graph every time and finding D blocks which are strongly connected, that itself will require some amount of searching. So, you can have a simpler way of doing that, like you sort the edges between nodes in the order of decreasing weights. You choose the heaviest edge, the edges are in decreasing order. Suppose you find that B1 and B6 they are connected using the strongest edge with edge weight 10, say. So, these are the two you put in the cluster. Then systematically you try to add more blocks to the cluster which are most strongly connected to this set B1 B6. So, this you go on doing successively till you get a cluster of size D. So, you take the heaviest edge, the two modules of the edge are clustered in a greedy fashion, and in this way you just add some more to this which are strongly connected to this pair, it becomes 3, then to the 3 you add another block, it becomes 4. So, the next high level, this set of D blocks will become a super block, and their weights to the other blocks will be the sum total of the weights of the constituents. Like from here you have a connection to B2, so you will the weight of this edge will be sum of the weight B1 to B2, B6 to B2 and all other nodes similarly. So, the edge weights will be summed up accordingly. So, even at the next level of iteration you do the same thing repeatedly, right. Okay.
So how will we find B2?
B2 we are not finding, we are saying that what we are saying is that suppose you have a graph containing B1, B2, B3, B4 and B5. Say in the say our D is 3, D equal to 3. So, you select B1, B2 and B3 in the first step because they were most strongly connected. Say this weight was 10, this weight was 8 and say this weight was 4, say. Suppose the other weights were 3, 2, 6, 4. So, this has now become a super vertex. So, the next level this super vertex will be there, in addition you will be having B5 and B4. B5, B4 are already connected with an edge of weight 6. Now, this will be connected to B5 with a weight which will be equal to 3 plus 4, 7, and this will be connected to B4 with a weight, well, only 2, there is no edge B2, B4 or B1, B2. So, this new weights will have to be calculated as the sum total of the weights of the edges from B5 to means each of the nodes in this cluster, right. So, in this way you go on repeating.
But some information is lost after we go every stage up.
Information is lost
Which
in
of the internal nodes?
Huh.
This the super node is being connected to this.
you see that information will be lost anyway, because once we have chosen to merge these 3 into 1, which means we have already said that we have finalized a portion of the floor plan where B1 is here, B2 is here and B2 is here, B3 is here. This we are not going to disturb anymore. So now if we say that we will be placing B5 somewhere here.
So because the selection of this, like how we place B1.
Yeah, I get your point. I get your point. I get your point. Where we
not connected near to B2 and B3. It is suppose beside B1. That will be problem.
true. B5 may be placed adjacent to B3.
Yes, sir.
Maybe, yes, yes, true. But at least they are placed, means you can somewhere close together, may not be they are having a common boundary between them, but they are placed in close proximity if you do this. But you are right. So means we are just we are treating this as a black box, and means we are losing some information regarding the details. Details means this B5 is connected to precisely which block. Yes, we are losing that. But our idea is that since we are taking the heavier edges before, so all the stronger things are together. The weaker things may be slightly further apart. Yes. But this method suffers from some drawback, as we will show with an example. See, here we are following a greedy approach, that all these stronger nodes or the heavyweight edges we are taking at the beginning towards the leaf, and as we move up, the weights of the edges are decreasing. So there may be some so called lightweight edges which we have chosen, which selecting at a much higher level. Some module which is very weakly connected to others, that we are selecting at a much later stage, right. Now this may lead to adjacency of two clusters of highly incompatible areas, leading to a gross wastage of total area. That we will see it with an example. I will show an example. There can be wastage of area in terms of the floor plan. Now a possible solution suggested is just a heuristic. So here it says that if the weight of an edge is too small, then at the beginning itself you assign it to one of its neighbor, so that whenever that neighbor is assigned, it will also take it with him. So it is not that these two nodes are strongly connected, rather these two nodes are very weakly connected, but one of them is small. This is the point to note. One of them is a small cluster, it contains very few number of gates inside. If one of them is a small cluster, then allow that small cluster to piggyback on a bigger one which is adjacent to it, maybe with a very low weight edge. So arbitrarily assign a small cluster to a neighboring cluster when the sizes will be too small for processing. So let us take an example to illustrate this, what we mean by this. Well, this is a given graph A, B, C, D, E with the edge weights as 10, 3, 3, 3, 10, 2 and 1. So according to the greedy approach, this A and B will be merged first, so also will be C and D. So AB and CD will go down together, then 3, 3, 3, 9, they will be put together, AB beside CD. Now since E has a weight of 2 and 1 to the others, so E will be taken last. But if E is a very small cluster, the placement will possibly, or the floor plan will possibly be something like this. So here you are wasting too much space. But in terms of that heuristic, what it says, if it is a low weight node, you try to assign it to some other node which is adjacent to it, but may not be with a very high edge, with a low in fact. So some means a low edge weight which will possibly cause it to be handled at a much later stage under normal circumstances. But what I do is that let E and D come together at the beginning itself. So here whenever you are assigning C and D together, you are assigning actually C and D together. Since D is smaller than C, possibly E can sit side by side with D. So, the total floor area will be less. So, otherwise if you follow a purely greedy approach, you may land up with a floor plan like this, however the area may be more, right.
So how do we know that E is a small cluster?
That information will be given now, because when you are doing a floor planning, I am saying that you are given the blocks Bi, Bj. So, each block will be having some width or height, or in terms of gates, number of gates, some information is given. Because here bottom up is a natural approach, but you can also think of a top down approach for floor planning. See here, from the top down approach, well, you are actually doing partitioning and floor planning together in this case. Given the overall netlist, you are carrying out partitioning. That is from the top you are doing, from the total netlist you are doing a partitioning to smaller netlist, again doing partitioning to smaller netlist. So, if we create the floor plan from that order itself, so as you are doing partitioning, you are also planning, that means on the floor where you will be placing them. This is the so called top down approach. So, each partition you are making through partitioning is assigned to a child floor plan, and you are doing this partitioning recursively to each of these child floor plans. So, as it becomes smaller and smaller. But the problem here is that, well, there are good algorithms for partitioning a given you can say graph into two parts, like you can use Kernighan-Lin algorithm. But best result will be obtained if we can do a KOA partitioning in general. For most floor plans, if we instruct 2, if you can divide into 4, 5 or 6 and accordingly place it at the high level, then break each of them up, because if you break it up into 2, most of the time you will not get a very efficient floor plan. But the problem is that KOA partitioning is a difficult sub problem in general. You do not have very good algorithms for doing very good balanced KOA partitioning. Balanced partitioning is not available. So, actually in practice we never do top down approach to floor planning like this. Rather we can do some kind of a combination. What kind of a combination? See, you start with the bottom up approach. From the given blocks B1, B2, B3 at the lowest level, you go bottom up, and beyond a point you will get certain bigger clusters. Okay. Now these clusters will be just union of certain blocks. Now you take these clusters one at a time and again do a top down approach. Well, there is no guarantee that this will always give a good approach, because the bottom up you are doing using a greedy thing. So, using greedy thing you are merging 10 blocks to get a cluster. Now again you take that cluster, using some good partitioning algorithm, try to see if you can do something better. From top again you move towards the bottom. But this is rarely used. People typically use a pure bottom up approach with some heuristic to improve upon the solution, or some kind of simulated handling or genetic algorithm, as I said. So, this particular method of hierarchical approach to floor planning, as you have seen that so essentially you combine the blocks systematically, and at each step you also keep track of some information regarding the floor plan you have generated so far. So, you go on merging the floor plans to higher and higher levels. Now, next we just finally look at the method of simulated annealing. So, simulated annealing, well, I am repeating, this approach is used in many steps of physical design automation because of the large search space involved and the way, well, these problems have been explored using simulated annealing and has been found to work very well. to give very good results. Now, in the floor planning problem also, simulated annealing have been tried out by many researchers, by many people. There have been several different ways of approaching or means of modeling the problem, defining the moves, evaluating the cost function, they have been evaluated. But what we will be discussing is a very interesting approach which was proposed by some gentlemen Wong and Liu. This is some kind of an indirect approach in a sense. Well, you recall that for the simulated annealing method you require, well, of course, the solution space to be explored, some way of representing the solution. You have to define some cost functions and some moves. The moves will allow you to go from one solution to another, and the cost function will allow you to evaluate the solutions. So, I am repeating. So, if it is a better solution you are moving to, you always accept. If it is a worse solution, you accept with certain probability. Okay. Now here we had seen earlier that for a floor plan we can have a slicing tree structure to represent the floor plan. Well, the method we are discussing right now is applicable only to sliceable floor plan, but it can be extended to include also the wheel structure. Right now we are assuming that it is a purely sliceable floor plan. So, the floor plan can be split only using horizontal and vertical slices, and you have a corresponding slicing tree. Now, this particular approach, what it says is that for every such slicing tree, well, you can represent the tree in certain ways. Here they use the postfix notation of representing the tree, and all the manipulation regarding movements they had applied on the postfix notation. So, actually this slicing tree whatever I am talking about, this slicing tree is a data structure which actually represents a floor plan. Okay. Now, so suppose you have a slicing tree like this. Let us take an example: vertical, horizontal, horizontal, A, B, C and D. So, what I am saying is that this is a tree, this can be represented in some standard notation. Here we are using the Polish postfix notation. This tree in Polish postfix notation will be A, B, H, C, D, H, V, where H and V are the operators. A, B, C, D are the operands. So, what I am doing is that in order to move from one floor plan to the other, we define moves which are actually some perturbations or modifications on this postfix structure itself. So, we modify this postfix structure in such a way that we get another postfix structure which represents a move, which is actually that will be corresponding to some other slicing tree, which in turn will be corresponding to some other floor plan, right. So, just let us introduce some notations first before going into that method. So, as I have shown in this illustration, H and V are the operators. So, in the Polish notation, the notations used are I, J, H, which means rectangles I and J are sliced using a horizontal line, which means I is on top of J. This means I is on top of J, something like this. Similarly, I, J, V means I is on the left of J, there is a vertical slice, right. And due to some reason which you will be understanding slowly, that we only consider normalized Polish expression in this problem. Normalized Polish expression means a Polish expression which does not have consecutive h or consecutive v. This example which you have taken, this is a normalized expression because h and v's are non-adjacent, 2h, there is no 2h or no 2v together. So, a Polish expression will be called normalized if there are no consecutive h's or v's. Roughly speaking, this is used for the purpose of removing some kind of redundancy in terms of the solutions. See, ultimately we want to explore the solution space, and we will see that corresponding to the same floor plan there can be several different slicing trees, slicing tree 1, slicing tree 2 and so on. Some of these slicing trees will be corresponding to normalized Polish expressions, some of these will be corresponding to non-normalized Polish expressions. For a vast majority of floor plans, there will exist normalized Polish expressions. Well, with the exception of trivial floor plans like this, there are two horizontal slices one after the other. So, for this you will not get a normalized expression, right. But for others you will get some slicing tree which corresponds to a normalized expression. Just in order to reject the other ones, to reduce the search space, we decide to concentrate on normalized expressions only, because for vast majority of floor plans there will exist at least one solution which will have a normalized expression. Now, by ruling out the non-normalized one, unnormalized ones, we are limiting our search space, that is all. Okay. The same floor plan can have more than one slicing tree. Let us take an example here. So, this is a simple example with 3 subblocks separated by 2 vertical slices, but one of them also separated by a horizontal slice. Now, you see that this particular floor plan can be represented by 2 alternate sequence of slices. Well, in the first one, the first slice is this vertical slice in the middle, then in one side you make a horizontal slice, in the other side you make a vertical slice. So, the Polish expression will be 1, 2, h. Well, sometimes while representing, h is represented by dash, v is also represented by a bar. H means horizontal cut and a vertical cut. So, 1, 2, h, 3, 4, v, v. So, there are 2 vertical operators which are consecutive. So, this is not a normalized representation, but in the other one you start with this slice first cut this, then cut this, then cut this. So, here you will be having 1, 2 horizontal, 3 vertical, 4 vertical. So, you look at this expression, you will find that there are no consecutive v or h operators. So, here the idea is that we, well, for most of the floor plans we will have solutions like this. So, in the algorithm that we will be discussing, we will be explaining it in the next class. So, there we will be seeing that we would be looking at only normalized expressions and we would be making some moves. And another thing, while we are defining the moves, we will see that there will be not a single way of defining move, there will be 3 alternative moves we will be defining, we will be selecting one of them at random. Now, out of those 3, 2 of them will automatically leave this expression into a normalized one, but only the third one can make it unnormalized. So, we will have to make some special check for the third move if you choose to apply that. So, for the third move, if you choose to apply that, we will we'll have to make it. Well, if we see that the move, if we apply, makes the equation non-normal unnormalized, we will not accept that move, we will select some other move again at random. So, in our next class, the first thing is that we will be discussing some more details of this algorithm regarding the moves. We will also illustrate the algorithm with an example. Then we will be moving on to a related, you can say related sub problem. Well, we had looked at floor planning. Next, we will be looking at a related sub problem, that is called pin assignment. Like say, for some of the blocks which are already designed, the positions and the definitions of the pins are already fixed. But for the blocks which are flexible, there is some flexibility which you have. I can put pin number say A and B like this, or I can even reverse them. So, I will try to optimally place the pins on the boundary of the block so that the routability and the routing cost gets minimized, right. So, all these things we will be discussing in our next class. Thank you.